Today we are going to start a new module, that is three-phase transformer. For this we are going to use generalized theory of electrical machine, which is written by P.S. Bimra, published by Khanna Publishers. The three-phase transformer is given in chapter 8, page number 798. So let us begin with three-phase transformer. We all know what is the role of transformer. Basically, the transformer is required to step up and step down the voltage. You will find out it is placed in generating station and it will be at receiving end. So there the voltage will step down, and then at distribution end you will find out the transformer. So this is a pictorial view from where you could understand that whether it is a single phase transformer or three-phase transformer, it is going to utilize at power generating station and distribution substation. Mostly the transformer is three-phase transformer, which is used at generating as well as distribution substation. Okay. So the purpose, it is already understood that it is going to increase or decrease the level of voltage. So basically from one level to another level, voltage is changed by means of transformer, or it could be three-phase transformer. When we talk about construction of transformer, so basically you can obtain three-phase transformer from three single units of single phase transformer. If you are having single phase transformer, just take three transformers, so it can be connected in certain fashion to obtain three phase transformer. So one way is to construct three phase transformer from three single phase transformer. What would be the another approach? Like a single phase transformer, it is having one core. So in the same way you can construct basically a three phase transformer which will be having a common core and it have three sets of winding for three phases. I think there is no doubt that the three phase transformer will be having three phases. So it has three phases, so you need three windings, one winding for one phase. So three sets of winding for three phases. When we construct three phase transformer from three single unit of single phase transformer, the three units of single phase transformer, at that time such construction is called as three phase transformer bank. It is called as three phase transformer bank. So in transformer bank, whenever this terms comes across you, so you could think about, okay, there are three single phase transformers are used for getting three phase transformer. From construction point of view, this transformer, three-phase transformer, again can be classified as core type transformer and cell type transformer. So let us talk about the three-phase transformer which can be evolved using three units of single phase transformer. So just consider three transformers, three single phase transformer, and you can place in this manner what you could see here. Okay, so in this case we have considered three single phase transformer which is of core type. Okay, so core type construction we are trying to get evolved for three phase transformer. So it is placed in this manner. So what you could see that when you are going to place the three single phase transformer, their yoke, it should be placed 120 degree apart. So you can see there is a difference of 120 degree between the yokes of transformer. You can call this as your transformer 1, this is your transformer 2 and transformer 3. So between transformer 1 and 2 there will be 120 degree, and here 2 and 3 120 degree. Similarly you will get it 1 and 3 120 degree apart. It will be placed basically. You could see here that this is basically your core of transformer 1, 2, 3, and this will be called as the central limb, because there are 3 central limbs. That's why we are calling it as 3 central limbs. And the windings, the P that stands for the primary winding, the S that stands for the secondary winding. So each transformer will be having primary as well as secondary winding. So that is shown in this figure. And in this central limb there will be a flux which is going to flow. So basically there will be 3 phase currents in 3 windings. So these 3 currents in 3 windings, they are going to produce working fluxes. So fluxes will be also 3. So there will be 3 phases flux which will be mutually time displaced by 120 degree. So these flux which is produced in transformer 1, 2 and 3, that is going to flow through their respective yokes and then through central limb. In this central limb, you would notice that whatever would be the resultant flux, that should be 0. It should be 0. It must be 0 in this resultant flux. You can think that when you are going to consider the phasor sum of these fluxes, so you are going to get that phasor sum equal to 0. The reason is they are 120 degree apart. So the phasor sum, you will get it 0. So in this central limb, basically there is no flux. When there is no flux, so what you can think, it has basically no use in transformer. So what we can do, this central limb that can be removed or eliminated, because there is no role basically. The central limb has no role. So what you can do, you can remove that central limb. So the question will come, what earlier we said that the flux, it is going to generate, suppose you are considering one first transformer, so it is generated here and the return path that will be from here. So basically it is from the central limb. So what would be the return path? There are 2 other legs apart from whatever you are considering. So the return path that can be from other 2 legs or 1 leg. So there is no need of basically the central limb, it can be removed. If we are constructing transformer, considering 3 single phase transformer, so the cost which is going to incur, that would be quite high. So we can say this type of construction that is expensive. So being engineer, what would be our approach? We are interested to come up with a transformer which gives economically, it should be economically beneficial, or its cost should be reduced. It should be low as much as possible. So how we can reduce the cost? Okay, so that is the question here. How it can be reduced? The one thing is that while constructing, you can remove the central limb, because obviously it has no role. Already we have seen that. So central limb, that can be basically removed. The second thing what you can do, you can reduce the yoke of second transformer. This is your transformer 1, 2, 3. So this yoke, that can be eliminated. It can be removed. And whatever course will be there, that is for first transformer, second transformer and the third transformer, it should be third, you can arrange that in the same plane. So what would happen when you will remove this and you are going to arrange it in one plane? So your figure that would be look like this. Basically your transformer that is going to look like this. So here, which will be called as the central limb, that will be called as this one. So basically there are three legs and the two yokes you could see here. Each winding, each leg is going to wound with both primary as well as secondary winding. So for one particular leg that is going to show you one phase, this would be give you the second phase, and this will give you the third phase. Okay, hope the things are clear to you till this time. So what you could observe here, that this particular central limb that is going to offer low reluctance path as compared to other legs. Okay, that would be one of the characteristics. The exciting current for the phase winding in the central limb, it is less than it is for the outer two phase winding. Difference in exciting current that does not have any material effect on the operation of the transformer. Whenever there is certain difference in exciting current in a particular phase of transformer, so it is going to impact, but that impact can be neglected. It is not that prominent or that effective, so it should be accounted. So yes, this will be a problem with this construction, but because the impact is not that prominent, so it can be neglected basically. Now let us talk about the cell type construction of transformer. So like we talk about, we have obtained three-phase transformer from three single-phase core type transformer. On the similar way, what you can consider three single-phase cell type transformer, and they can arrange in a fashion where the three single-phase cores, they will be placed side by side. You could see in this figure that this is your one transformer, this is your another transformer, and this is your another transformer. So basically you can say the three transformer, its cores are placed side by side. You can notice here we have shown here winding. So this is winding for phase A, winding for phase B, and winding for phase C. Okay, and the flux which is produced, you can consider also there will be four section. This is called first section, this is your second section, here it is third section, and this one is your fourth section. Okay, and the working flux which will be produced in this winding, that is shown here. So you can see that the flux, it is phi A which is flowing, hopper flux is flowing here, and hopper flux which is flowing here. You can see the phi B is flowing in this way here, and phi B is also flowing in this way. The direction of the flux, that will depends upon the direction, in which direction the winding is wound basically. Okay, so depending upon that, the flux direction can be indicated. You could notice here that all the windings, the three windings, they are wound in one direction. You could notice that. Okay, so this is one observation for this particular figure. So what you could see here in this arrangement, basically the resultant flux that will be equal to the phasor difference of the component fluxes. Basically we are talking about, you could see that in this section, particular section 2, there are flux due to you can say the first transformer or transformer A, and there is flux due to transformer B or the second transformer. So what would be here the resultant flux in this section? That will be the phasor difference of the component flux. Why we are seeing the phasor difference? Because you could see the direction of the fluxes. What is the direction of the fluxes? For this it is on upward direction, here it is downward direction. So what would be the resultant flux here? That will be given by the phasor difference. Okay, so suppose in this section 2 we are saying it is a flux phi 2. It is the resultant flux is phi 2, and the flux which is produced in transformer A, in this section it is going to flow half of the flux, so it will be phi A by 2. Similarly, from this transformer B at the second transformer, how much flux is flowing here? That will be your flux phi B by 2. So resultant flux phi 2, that will be the phasor difference of these two fluxes. So phi 2, that will be given by phi A by 2 minus phi B by 2. If you want to draw the phasor diagram, so what you can do, you have to take a reference. Suppose here we are taking reference as a phi A. So phi A is taken as a reference. Then you can draw the flux phi B after 120 degree. Phi B is drawn, and after 120 degree from phi B you can draw the phi C. We are interested here to find out the flux in section 2. So in section 2 it is given by phasor difference of the flux due to this transformer A and the transformer B. So we have already seen it will be phi by 2 minus phi B by 2. So if this is phi, so you can get phi A by 2 in middle. You are going to get phi A by 2. Similarly, you are in position to get phi B by 2. But you are interested in minus negative value of phi B by 2. So how you can obtain? You need to extend this phasor in reverse direction. Then just take the phasor sum. It is going to give you phi by 2. In order to determine its magnitude, what is actual magnitude of flux in section 2, what we can do, we can substitute its value of phi A by 2. So basically we have considered phi A as a reference, so its magnitude can be considered as phi angle 0 degree, and for phi B it will be your phi angle minus 120 degree. Then we can replace this in this form, and after substituting the value of cos 120 and sin 120 degree and simplification, what you are going to get? You are going to get phi by 2 into 3 by 2 plus j root 3 by 2. The magnitude can be determined in this way. We all know how it can be determined. So ultimately what you are going to get? You are getting root 3 by 2 phi here. So what is the flux, the magnitude of the flux here? That is root 3 by 2 in this section. Similarly, what you could see in section 3, the same situation or the same condition is here for the section 3. That is the flux due to the phase B or the transformer B, that is in upward direction, and in phase C or in third transformer, here it is in a downward direction. So the same situation will be there. In the similar fashion, what you could do, you can determine the magnitude of phi 3 or flux in section 3. So what would be its value? Its value you are going to get it root 3 by 2 phi. What you could see here, that in these two sections, section 2 and section 3, the value is same. And how much is flowing in the section 1 and section 4? It would be this much flux. That is due to your phase winding. How much it is going to come here? At this section it will be your phi by 2 basically. Here how much it would be? Phi by 2. Okay, I think there is not any problem. There should be no problem. If there is any query, you may ask. Okay. So what we have seen here, that the flux in section 2 and section 3, that is root 3 by 2 phi. Here it is basically phi by 2 and phi by 2. So basically what it is indicating when we are talking about phi 2 is equal to phi 3. So we understand, or we can conclude, that if there is same flux density in cross sectional area 2 and 3, which will be basically here 86.6%, how you obtain this value, just substitute, simplify it, so you will get it 0.8665. so it will be your 86.6% of the central core area. So what is phi here? Basically phi is nothing but phi A equal to phi B equal to phi C, you can say. And the flux which is carried in this section, already we said that is a phi by 2. It means what we understand that it is the 50% of central core area. So in other words, we can conclude that the area of section 2 and section 3, they are 1.732 times the area of 1 and 4. Now we are comparing with this area. Whatever is the area of section 1, core area particularly we are talking about the core area of the section 2. When you are going to compare it, so you will find out the core area of section 2, that is 1.732 times the area of 1. Basically we studied the losses. Core losses are constant losses, iron losses. There your flux density impacts basically the losses that we have seen. That's why this becomes an important things which we should keep it in our mind. Okay, then let us move on further. Earlier what we said, when we considered the 3 transformers and cell type transformer particularly, at that time we said that all the windings are wound in same direction. But if winding of one of the transformer is reversed, in this particular case we have considered this transformer. Okay, here if winding is reversed, so what would happen? Is there something would be changes in transformer functioning, or what else impact would be there? So let us try to find out the question to this. So what we will do, we are going to reverse the winding direction of winding 2, on which direction it is wound, basically that would be the reverse. So what would happen, the flux which is produced by this transformer, its direction is going to be changed. Okay, so in previous case you could observe that you have seen that the flux which was due to this phase B or the central transformer or the second transformer, that was in downward direction. But here what you could see that it is in upward direction. So what would happen, the resultant flux in this section, that will be basically addition, phasor sum of the flux which is produced due to phase winding A and phase winding B. You could say that, or you can consider it as transformer, first transformer and the second transformer. So the resultant flux here, that will be the phasor sum of phi A and phi B. So phi A by 2 and phi B by 2, that is going to give you the resultant flux in this section. Here you could see that again the direction, both the direction, that is in downward. The fluxes, the resultant fluxes due to this phase B and phase C, that is in downward direction, means in the same direction. Again the resultant flux, that will be the phasor sum of the fluxes, flux component in this section. So let us find out its value and you can also draw the phasor diagram. So the phasor diagram that can be drawn by this way. Okay, I think there is not any issue. So similarly, similar to the previous case, what you can do here, we have considered the phi A as a reference. So just we are going to substitute its value. So what it will become, phi angle 0, then the phi B, it will be phi angle minus 120 degree, then convert it and substitute its value, corresponding value, simplify it. So how much you are going to get? You are getting the phi 2, that is equal to phi by 2. It means how much flux is flowing here? That is phi by 2. In previous case it was root 3 by 2 phi. You can say phi, that is equal, we have considered basically phi equal to phi A, phi B, phi C. So basically here how much flux is flowing? Phi by 2. In the same way we are in position to determine the flux in this section 3, the resultant flux. So you will find out it is also coming phi by 2. It means in section 2, section 3, the flux is flowing phi by 2. And how much flux is flowing in this section 1 and section 4? That is also phi by 2. So in all the sections, the flux is flowing here phi by 2. So basically what we understood here, we can conclude, we can understand that area of cross section of the portion 1, 2, 3, that will remain same. The core area, whatever will be utilized for all the section, that will be the same here. It is equal to 1/2 of the central limb area. So ultimately, when there is equal fluxes in all the section, so we can achieve economy of core material. That is possible with just reversing one winding. However, reducing cross sectional area at section 2 and 3, it is going to result in slight unbalance in the exciting current. If there is unbalance in exciting current, so it is going to create some problem, but its impact, practically it is found that its impact is quite low on which the operation of the transformer. So it can be again neglected. So this type of construction, if we are going with such type of construction in case of the cell type transformer, so what you can achieve? You can achieve economy of the core material. And when we are talking about economy of the core material, it means you are in position to reduce the cost of transformer. So that can be achieved. This could be one probable question which might be asked in by examiner. They may give you this type of construction and they will ask you in which construction you are going to obtain the lower cost of the transformer. So that could be one of